Okay, so we are continuing our discussions. Last time we have covered power spectral density, last lecture. So again, if I construct, let's say 1 Hz bandwidth filter, 1 Hz. So this is my 1 Hz bandwidth filter. Let's say that I change my 1 Hz bandwidth filter center frequency from this frequency, DC. I put this 1 Hz filter over here and move it like this. Okay, I'm scanning the spectrum. You may think about it like that. So if I have a random process over here, okay, then I have another random process, filtered random process at the output. And if I just, let's say, calculate power of this output process, then what do I see? So over here, my filter is at this point, there is no output. I move my filter like this, and it, let's say, covers this. Suddenly, I see this much of power at the output. Okay. Then if I move it like that, that is capturing the second component, and so on. So by scanning this spectrum, so again, something very practical as you see, I'm getting distribution of the power of this input process along this frequency axis. Okay. Along this frequency axis. So I see that this total power of this process is distributed according to, in the earlier example, according to this distribution, which is discrete, which has capital K units over here. So that is the conclusion, but let me write a few notes. Number 1, so let me write LTI filtering of white noise, but WSS, white stationary white noise, with a filter having magnitude response h of f results in n, let me see, output process in an output process with power spectral density S x of f is equal to, this times this. So this is the variance of white noise. This is this. So we see that hence, by designing filters, we can, in quotations, shape a white noise process into other processes by filtering operation. In practice, the data is collected and from the data, autocorrelation or power spectral density, let me use blue color, of a random process is estimated. Again, as I have said, now you don't know the autocorrelation. No one, in practice, no one gives you these autocorrelation sequences or power spectral density, let's say function, and so on. Okay? So no one gives you that. So these are, it's estimates. So these are the estimates. Somehow, I'm capable of estimating this. So in practice, data is collected, this is estimated. Okay. We aim to synthesize the estimated let's say autocorrelation, let me write it like this, and slash or as x of f, again the estimate, by properly designing an LTI filter such that when excited with white noise, its output has let's say autocorrelation or power spectral density as it has approximately the measured quantities. So let me check this sentence. Okay. So let's see. Hence, by designing filters, we can shape a white noise process into shape vertex in quotations. By filtering, we can shape the white noise process into other processes. In practice, data is collected by an experiment and so on, and from the data, autocorrelation or power spectral density of a random process is estimated. These are the estimates. Okay. We aim to synthesize the estimated autocorrelation or power spectral density by properly designing an LTI filter such that when excited with white noise, its output has autocorrelation or power spectral density approximately realizing the measured quantities. Okay, so actually it says just the following. If I have white noise over here, white noise, W of t, so I design my filter, H of f. Now this, let's say x of f, x of t. Now this x of t, this is white noise. Now this is y sans stationary, and I know that as x of f is as w of f times this h of f magnitude square. So let's say that I have some measurements for this. Measurements. So this is white noise. So this is just constant. Y sans stationary. White noise, this is just constant. Then this is called the synthesis problem. If you have some measurements for this, now how can you generate this process or how can you understand this process? You can say that this process can be modeled by matching the power spectral density. So this is my measurement. So this is the white noise. So essentially, I'm trying to find a filter such that whose magnitude square is equal to this, okay, your measurement. So if I can design such a filter, even approximately, that means that I can synthesize this random process having the same power spectral density. So this is called the synthesis problem. Synthesis problem, i.e., given this or Rx of tau, find a filter, find LTI filter such that its output has autocorrelation, let's say, almost equal to Rx of tau. So white noise input, under white noise input. Unfortunately, it's difficult to write under white noise input. Or we study this in some other courses. This is called, spectral decomposition of the filter and so on, of the process and so on. Okay, but not in this course. This is one of the applications. Now, I would like to say one more thing about white noise. Now, you didn't ask me, why do we call this, this Do you remember? If I have autocorrelation, impulsive autocorrelation over here, I was expecting someone to ask me this, but no one has asked me. So this is white noise autocorrelation. Am I right? White noise autocorrelation. So nobody has asked me why this is called white, and what is white about this. How about this? If I take its Fourier transform, what do I get? Power spectral density of this white noise. Am I right? And it's just flat. Am I right? It's Fourier transform. So this is frequency. So this is power spectral density of white noise. Now, is this clear? Why do we call this white noise? Because the color white is containing all the other colors, isn't it, in the spectrum? And those colors are actually frequencies. Those colors are actually a radiomagnetic wave at different frequency. All of them are electromagnetic waves, okay? Radiation, essentially. So this is the reason that we call this white noise, because it contains all the components in the spectrum, as you see, in this Fourier, in this axis, in the frequency axis, in the Fourier domain, at the equal weights, okay? So this is the reason that this is called white noise. It's containing all the frequency components, okay? But of course, this is just, a catchy, let's say, phrase. I mean, it has nothing to do with light and etc., obviously, okay? But this is just a nice phrase summarizing that this white noise contains all the frequency components possible with equal weight. It's just flat, overall spectrum. So what else? Number 3. Let's see. So this is supposed to be 3. So previously, we have stated some necessary conditions for the validity of autocorrelation sequence or autocorrelation function. Maybe you can remember. Rx of tau, a valid autocorrelation function. Now we say that, for example, something like this. Rx of 0 is greater than or equal to 0. What else? Rx of tau is equal to Rx of minus tau conjugate, etc. Things like this. Okay. So these are called necessary conditions. Actually, we had a discussion about this. Now we have another necessary condition. Which is Rx of tau, a valid autocorrelation function. And we say that its Fourier transform, Sx of f, is positive valued. I mean, these are the properties of the autocorrelation, isn't it? It is real valued, non-negative valued, okay? That is it. Its weight is equal to the total power of the process, etc. Okay. So this is another necessary condition. So what is unique to this condition is, well, let me say, but unique to this condition that is SS power spectral density being non-negative, we can show that it is also a sufficient condition. This is different. Sufficient condition for a valid autocorrelation. For a valid, I think it will be clear, Rx of tau. So what do I mean by this? Now previously they were all necessary conditions because I was starting from here, deriving some properties from this one. Okay. Now the issue is if this is satisfied, meaning that this condition is satisfied, I am sure that I can find a process with autocorrelation, a valid autocorrelation. Okay. With autocorrelation Rx of tau matching that. So let me first explain this. So hence, this time we have Rx of tau, a valid autocorrelation function. So I have Sx of f, which is the Fourier transform of Rx of tau. This is greater than or equal to 0 for all frequencies. Maybe I should write for all frequency over here. Okay. Now two things. So first of all, this should be satisfied. If this is satisfied, I am sure that this thing, inverse Fourier transform of this, you may say. Inverse Fourier transform of this, Rx of tau. Rx of tau, inverse Fourier transform of this claimed power spectral density is indeed an autocorrelation function. Okay. So this is the sufficient condition. The arrow is reversed as you see. Okay. Sufficient condition for a valid autocorrelation function. So if somebody gives you a function and if that person claims that this is an autocorrelation function, then how do you test this? Now you can say that, okay, let me calculate its Fourier transform. Okay. If that is positive, right now we have this. It's both necessary and sufficient. So they're equivalent. So this becomes necessary and sufficient conditions, this if and only if statement. Okay. So positivity or non-negativity of this power spectral density implies this, and the valid autocorrelation function implies that. We haven't shown this actually, but this is a fact. So if somebody gives you, if that person claims that it's a valid autocorrelation function, you can do this check. Valid autocor. You can take the Fourier transform of this. It's an easy check, isn't it? If you take the Fourier transform of that, if this is indeed greater than or equal to 0 for all frequencies, then you are sure that it's a valid autocorrelation function. Okay. The reason is, now this is a sufficient condition to say that this is true. That is it. So we are not proving this. So in, let's say, let me see this. In Populus, let me see. Section 1024, page 322, an example is provided. Such that given a GF function which is G of f greater than values greater than or equal to 0 for all frequencies, it is possible to have a process, not possible, but Populus actually constructs that process. Populus constructs an x of t process such that its power spectral density is G of f. Okay. So this time Populus does the following. If I have a function which is always non-negative, then Populus treats that function as power spectral density function and constructs a random process x of t such that it is indeed the power spectral density. So for any G of f, I can always construct a process. And this is what I want actually. Because given this, right now over here, given this is satisfied, I can construct the process with autocorrelation or power spectral density, exactly that. Okay. So this is what we want. So this is, I mean, this is nice to know, but we are not interested in the proof of this. Just I'm mentioning it because of its importance in terms of validity of autocorrelation functions and its relation with power spectral density. What else? One more thing. This is number 4, I guess. Number 4. So power spectral density allows us to classify random processes as low pass, high pass, / bandpass. Bandpass processes. So as in, let me put it over here, as in conventional filter specifications, LTI filter specifications. So a process is called a low pass process if its significant amount of energy, amount of power resides in low frequencies, I mean something like that. So is this clear? Now we have the concept of low pass filter, high pass filter, signals with occupying high end of the spectrum, Fourier spectrum, and so on. Okay. So we can extend those ideas to the processes right now. Low pass process, high pass process, band pass process. The issue is again this. Now you have a process, you have a low pass filter over here. So this low pass filter, at the output you observe a significant amount of power over here in comparison to this. Then you say that, okay, my process is a low pass one. Okay, that is the idea essentially. Well, this is good. This is good to know. So next we will be studying bandpass processes. This is our final topic actually in this course. Bandpass processes. And that is the end of power spectral density discussions actually. And we are switching to bandpass processes. Representation of bandpass signals / processes. Actually, bandpass signals and bandpass processes will be important because of their telecommunication value. For example, you are listening to radio METU. What is the frequency of radio METU? 103.1, am I right? Megahertz. So that's a bandpass signal. So you are listening maybe 200 kilohertz or 300 kilohertz, etc., around that bandwidth. Okay, bandpass signal. So we will be studying such signals, but in the spectrum there is also noise. So that would be the bandpass signal radio METU plus maybe noise over there, maybe something else. So how can I model those bandpass signals and bandpass processes? That will be our final topic in this course. But let me see. This is over here. So let me write this. Before bandpass signal discussions, we need to study something actually quite simple, but we need to study this Hilbert transform, which we need along the way of our study. So let's start the Hilbert transform discussion. This is something, don't worry, it's something very easy to understand, Hilbert transform. Now, x of t, again I have an LTI filter with impulse response, this is pi, 1 over pi t, and I will call this output as, so this will be the Hilbert transform of x of t. So we'll be using this hat over here to denote Hilbert transforms. Previously, maybe in note number 2, I guess, I have also used hats for the estimates. But this is not estimate. This is the output of this block. It's called the Hilbert transform of x of t. Okay. Now you may wonder what kind of transformation is this? This is nothing but a simple, filter. Indeed, you are correct. This is nothing but, a simple filtering operation. But why is this important? You will see immediately, because it's a rather, a unique kind of filter. So, but let me write first of all this relation. Output is equal to convolution of the input with the impulse response. Am I right? Output is equal to this. Okay. That is it. Now questions comes up. So is it an invertible operation? Is it an invertible? Is there an inverse Hilbert transform relation, etc. and etc. Now how about this? If I apply this, Fourier transformation one more time. So this is the Fourier transform. X of t's Fourier transform is x of f. Now how about, this is difficult to find, but 1 over pi t's Fourier transform. This is actually minus j signum f. So what's going on? So this is the signum function. Signum, let me write x. So if x is greater than 0, it is 1. It's a sine function, 0. And x is less than 0, it's minus 1. So as you see, it's a very unique kind of operation. So how do I derive this? Derivation of this one is, again, somewhat like tricky, but it's possible. Okay? I will explain maybe later on, but let's accept this for a while. Okay? So a little bit tricky because of some considerations, but let's do not get distracted. Let's accept this. And then what do I have? Well, I see that now if I take the Fourier transform of this, so how do I denote this? I'll be denoting this capital X with hat of f. Okay? So this is convolution theorem. X of f times, this h of f. H of f is this minus j signum f. Do we agree? That is it. Okay. So this is Hilbert transform of x of t in Fourier domain. Or this is the Fourier transform of, you may say, Hilbert transform of x of t. Am I right? So this is my small head function in time. Okay, that is it. That's what I have. Now, given this, we can first observe that so if I have x of t 1 over pi t, this is the output. Now, if I have one more Hilbert transform, 1 over pi t, what will be this output, second output? Maybe you should use this. What will be the question mark? It's the negative of it, isn't it? Why do you say it is the negative of this? It's actually minus the original, the very first input, x of t. Because the reason is, well, if I have two filters in cascade, the transfer function is individual transfer functions multiplied, h1, h2 in frequency multiplied. And I see the following, minus j, signum f, parentheses square is equal to, do you see what I mean? So signum f is, let's see, so this is, let me write like this. It's a little difficult to write this, j signum f. So over here I have minus j, let's say, this is j, okay? Or let me write just signum because it's complicated. This is distracting us. 1 minus 1, I have 0 over here. Okay, minus 1 squared is equal to 1. J squared is equal to minus 1. Okay, signum f squared is equal to, well, whatever the value of f is, it's always 1 except 0. So this is equal to minus 1, as you see, provided that I'm not interested in the 0 frequency. Okay, that is it. If we don't count the 0 frequency, then we have this. So whatever happens at 0 is not very important in this Fourier transform discussions because it's just a single point. Okay, single points are not important. You can define this value if you wish that or that, doesn't matter in terms of integration. So what we have is that from here to there, I have such a connection. Now I think we are done because what we see is Hilbert transform sorry, this is tau, t minus tau, d tau, and the inverse of it. So what is the inverse of it? So if I multiply, this one by minus 1, then I get x of t back, okay? So it is almost like the same operation. So let me write it better. What is this? So this is forward and inverse Hilbert transforms. Okay, that is it. So only thing that I made use of is this Fourier transform relation actually. That is it. So this is tau. So this is nothing but this convolution. And from here to there, I have almost like inverse Hilbert transform, but to have the inverse transform, I should put a minus sign, then I have plus, okay? By the linearity. This is the reason that they are exchanged at this point, okay? Because I'm convolving it minus, minus of this one. That is it. But in order not to complicate this, let's say minus 1 over here. Otherwise, it will look tricky. Now, what else? Now, this is this. So let me write a note. Note, Hilbert transformation, Hilbert transform by convolution operation is not feasible or implementable in practice. So terrible news, isn't it? I cannot implement this. Why do I say so? Since h of t, 1 over pi t, so this is the impulse response, is not absolutely summable. Absolutely summable, i.e. corresponds to an unstable filter. Terrible news. Unstable filter. So what do I mean by that? If I design a filter like this, now this is an unstable filter. If I process this, I'll be getting some output, but due to filter being unstable, there will be some, let's say, initial, there is no steady state, that kind of definition, that kind of concepts over here. So if there is some uncertainties or mismatches over here, there is some noise effect, it will be significantly affecting the output because filter is unstable. So what's going on? Why are we discussing this? The Hilbert transform is used mostly as a tool for analysis just like, let's say, Dirac delta function and u of t unit step functions, etc. If you think about that, even the unit step function is not absolutely summable. Okay? There are things like that. So this is one of those tools, another tool that we'll be using. So this is just a remark. Now, let me find my notes. Let me have an example on this. Perhaps you would like this example because it will tell us something about the operation of this Hilbert transform. Example. So let's say that let x of t cosine 2 pi f naught t. Okay. So question is find x hat of t. That is it. Of course, I don't want to do it with convolution, as you can imagine. I don't want to convolve this with 1 over pi t, because I don't know how to do that integral. Okay, that will be a very, very tricky integral. So how can I do this? Now solution. Okay, now I see, okay, let me sketch this, x of t, because we are new to this, 1 over pi t, and I have this. So this is equal to a cosine 2 pi f naught t. Okay. So how can I do this one? So let me do it graphically. So can I sketch x of f? This shouldn't be very complicated, x of f. So this is the Fourier transform of cosine 2 pi f naught t. So what do we expect? So this is the frequency. Now I have f naught 1 over 2 minus f naught 1 over 2. Okay, that is it. So how can I find the, Fourier transform of this one? So let me do the sketch of this. This is the Fourier transform of 1 over pi t. As we have said, this is minus j signum f. Okay. So how am I going to sketch this? This is f. Okay. So I should write here I don't like this sketch because it's very confusing. 1 and minus 1. And I don't want to write just signum f then. let's write signum f only, because it may cause us confusion. But let's keep this over here. 1 over pi t minus j signum f. Okay. So what's going on? I should multiply this by that, and I should sketch graphically this Fourier transform of the output. Okay. So this times that. So what should I do? I think there are two impulses again. Okay. So what is the weight of this impulse? So it's multiplied by 1 over here and multiplied by minus j. So can I write this one as 1 over 2? Let me put j like this. I'm putting j in the denominator. I can do it this way. This one is multiplied by this part. So everywhere it's 0 except this impulse location. Okay. So this is minus over here, but actually it's negative of that, because only changes this is multiplied by 1, this part is multiplied by 1, this part is multiplied by minus 1. So I get minus 1 over j, like this. Okay. Now, what do you think this corresponds to in time domain? Exactly. So this corresponds to, that was very fast. This is the reason that I got surprised. Maybe you are getting a little bit sick of this long lecture. You are being very fast. 2 pi f naught t. Is this correct? Okay. Why? Well, I think it's clear that this is the sine 2 pi f naught t. So it's a little bit interesting. So a cosine is, with this operation, converted into a sine. Let me use this a little faster. So let me do it, using not graphics, but it's essentially the same by multiplication of functions, just as an exercise. Just let's say algebraic, let's say. This is the same operation, but I'll be doing it algebraically. So what do I mean by this? This is equal to inputs Fourier transform times, let me write one more time, Fourier transform of 1 over pi t. Okay? So let's insert Fourier transform of this cosine. Well, I put a over here, so this is 1. This is not a, because in the problem it's 1. Okay. So this one is 1 over 2 delta f minus f naught plus f plus f naught. This is equal to this. And the other one is equal to this. Okay? The other one is equal to this. So we are at this step. This. Now I multiply them, but I multiply them algebraically. So how do I multiply them? Let me put this minus j in the denominator one more time. Let me put 1 over j2. Okay. Let's move this j like 1 over j over here. Now I have signum f delta f minus f naught plus signum f delta f plus f naught. Okay. So let's assume it doesn't make much difference because of this cosine, but f naught is greater than 0. I mean, let's specify it. It can be negative, doesn't matter for the cosine, as you see. So let's say that f naught is greater than 0. The reason is, at the end of this multiplication, this part, what do I have? Signum f naught delta f minus f naught. Let me write better. Actually, this is this part. This and this multiplied. I have a Dirac delta at the same location, but weight is changing by this multiplication. I have that. Now this is f naught is greater, so this is equal to 1. and this is equal to minus f naught. Okay, so this is equal to minus 1. So we are there. Okay. So as you see, 1 over j2 delta f minus f naught minus f plus f naught. And if I take the inverse Fourier transform of this, then let me write inverse Fourier transform. It's indeed sine 2 pi f naught t. Okay. So both of these interpretations, I mean not an interpretation, but calculations are important. Because in many cases, you deal with these sketches. And for exact, let's say, this kind of manipulation, we should understand how this signum function affects. Okay. Both of them are important for our purposes. Okay, so that will be all for today. We will continue with more discussions in the next hour. Okay.